All right. You remember we talked about functions some time ago. So here are some graphs. If this is graph A, graph B, graph C, graph D, and graph E, how do we determine if these things are functions? Good, the vertical line test. If I take a vertical line, find a tool that looks like a vertical line. Please keep the side conversations down. And if I pass this vertical line over the function, over the graph, you guys stop talking, please. I want to see if it only touches in one place. So A passes that test. Therefore, it's a function. What about B? Also passes. What about C? What about D? Does not pass. At that point, my vertical line hits in two places. What about E? Okay, so we know that this is a function, this is a function, this is a function. These are not. Agreed? Now let's talk about one-to-one functions. Do you remember what one-to-one functions are? Good, inverse. In other words, that means that both the original function and the inverse are in a one-to-one relationship. Which means, for example, if I were to take this graph, some crazy looking graph, and I wanted to graph the inverse, we would have to say, here's the line y equals x, and we'd then be expecting a graph that looks like this, but is a reflection over the line y equals x. Those are inverses of each other. And if we plotted the inverse, we'd want to see if it passes the vertical line test. So does our original one here pass the vertical line test? And does our new one here also pass the vertical line test? Therefore, this passes both and becomes a one-to-one function. There is a shortcut for doing that. Do you remember? Instead of having to actually graph the inverse and look to see if it passes the vertical line test, that is the way you graph it, is swap the x's and y's. But I'm thinking in addition to a vertical line test, there's also a horizontal line test. So if this passes both the vertical line test, establishing it's a function, and the horizontal line test, establishing that its inverse is a function. So is A a one-to-one function? Is B a one-to-one function? No, because if I were to graph that as an inverse, this is always hard for me. I have to choose points. Like this is 1, -1. So that would be -1, 1. No, that's -1, -1, isn't it? That's right. -1, -1. And then this is the point, say 1, 0, which means 0, 1 would be up here. This is the point like -3, 0. So 0, -3 would be here. And then this point like -5, 5. So 5, -5. It would come out looking something like that, right? And it wouldn't pass the vertical line test as an inverse because it doesn't pass the horizontal line test as the original function. Is this one-to-one? No. Just one-to-one? No. These aren't even functions, so they can't be one-to-one. All right. Does that ring bells? That's where I want you to start in your head so that we can talk about these functions. What graph does that sort of look like, except for that tail that went off wonky? Looks like the sine function, could be the cosine function too with that transformation. But as a parent function, that's sine, right? Does it pass the vertical line test? Because really it goes on forever in both directions, doesn't it? It passes the vertical line test. So it's a function, yes. Is it a one-to-one? No, because it does not pass that horizontal line test. What that means is that the inverse is not a function. So if I take the function f of x equals sine of x, how do I find the inverse? First change f of x to y, then swap x and y, and then solve for y. So if I want y to be all its own, what's being done to y right now? It's being signed. How do I undo that? Arcsine, right? I could do, we write it as sine to the -1. I make jokes about it being dissinification, anti-sinify, but it really is called the arcsine. And what we're saying about this function is that it's not a function. Yes.
Is arcsine different from cosecant?
It is. And I know the notation is confusing, right? Because -1 also means 1 over as a reciprocal function. And that's why I'm now calling it arcsine, so we don't get confused about that. So this is the undoing of a sine application. What is sine? What does sine do for us?
Finds the update in the unit circle for some angle measure.
Yeah, but the unit circle is a specific application of it, right? Like you guys learned about this in geometry before we had the unit circle. And the trick is when I want to describe what angle this is at, I have two ways I can do it. I can either describe specifically the measure of this angle by radians or degrees, or I could leverage the idea of, well, it goes over this much when it goes up this much. Or when I go up this much, the hypotenuse ends up being this length. Like if you're building a sidewalk and you want to make the sidewalk exactly 20 feet long, but you can't have it go up more than 3 inches in 20 feet to make sure that it's not a tripping hazard or somebody's going to fall down. You could describe it that way. And most people who build things do go by ratios of sides rather than angle measures. What sine does is it takes an angle measure. When you sinify it, it turns it into a ratio of sides. Right? Sine takes an angle measure and changes it into a ratio of sides, ratio of lengths. And we know that this always is a number between -1 and 1, because we know that the sine as a function always has a range between -1 and 1. With me? Which means the arcsine does what? It takes a ratio of side lengths and says, with those side lengths, this is the angle that's in that triangle. It goes from a ratio of side lengths to an angle measure. Agreed? So let's say that, for example, I wanted to take this point. Can you tell me what this point is? The y value is -1, good. And let's go in degrees. That's 360. That's 540. So 630. Do you guys agree that's 630 degrees, comma -1? Which means if I take my calculator and I were to plug in sine of 630 degrees, make sure my calculator is on degrees. I do sine of 630 degrees. What do we expect the answer to be? Okay. So what if I wanted to use the arcsine function, the inverse sine? I would, sorry, not tan, over here, arcsine. If I take the inverse sine of -1, that would tell me the angle, right? But here's the problem. Does the calculator know that I'm in this group? What's this value? 270, -1. And in fact, there's infinite more values, aren't there? Like over here, I've got -90, -1. Agreed? So what's the calculator going to tell me? What do you guys think? What's your 270? Raise your hand if you think it's 270. Two of you. Raise your hand if you think it's 630. No one. Raise your hand if you think it's negative 90. No one. Raise your hand if you are so not willing to commit to this because you have no idea. There go a bunch of hands. Okay. When I hit enter, I get negative 90. So here's why. Sine is not a one-to-one function, is it? Which means when I look at the reciprocal of that, sort of like, not the reciprocal, sorry, the inverse of that, it's not a function. Which means when I plug in a single x value, I could get a bunch of different y values. We don't want that. So instead, what I need to do is take my sine function and find a portion of it where it allows me to see all of the possible y values. As I come off of 0, do you agree that these are the possible y values that are positive? And then I wouldn't want these because these repeat it, right? But now we're getting from here, an open circle, down to there. Would you agree that that domain would give me all the possible y values? That would give me a one-to-one relationship. But if I were to write this, I'd say, okay, 0 to 90, union 180, actually, and these are inclusive. This is exclusive to 270. Isn't that kind of a brutal looking domain to begin with? Is there a better way we can get all of the y values in a nice contiguous section? Isn't that nice? In other words, if we set our domain, if we restrict our domain to be from negative 90 inclusive up to positive 90 inclusive, in other words, negative pi over 2 to positive pi over 2, doesn't that give us a nice comprehensive arcsine? And then once we get those values, we've got our reference angles. And as you've been working on recently, you'd be able to evaluate what it means. Like when we did the inverse sine, arcsine of -1, and we got a value of negative 90, we could say, okay, I know that's over here, but I know my relationship such that if I want it to be in this, I'm going to have to add on cycles, versions of 360, and I can get 270, and then, okay, I could add on another 360, and I get 630, and that'll be the same value. Does that make sense? We'll use our calculators with this information pre-programmed in, and then our brains to figure out how we transition to the actual answers we want. All right, so let's take a look at this. We're going to start by graphing the sine function, f of x equals sine of x, but we're not doing the whole thing. We're restricting our domain into that realm we just talked about. So I'm going from negative pi over 2, which has a value of -1, up through 0 to positive pi over 2. In other words, I'm only providing this much of the graph. And make sure you get those little swoopy curves in there. And if I want to transition that over to my arcsine, remember how we do this? How do we change a graph into its inverse? Well, it reflects over the y equals x line, but it's easier if we think about it as changing the x and y values, right? So this point is negative pi over 2, comma, -1. So over here, what would be the corresponding point? Switching the x and y gets me to that point. And 0, 0, take me to that point. And pi over 2, 1 would take me to 1 pi over 2. So it gives me the 3 points, but I got to make sure it looks the right swoopiness. So this one is the sine curve running left and right. This one's going to be the sine curve running up and down. So I'm expecting this is going to look more like this. Please do your best to show the swoopiness doing the correct things. Concave down to the left of 0, concave up to the right of 0. And again, our little sub function of sine has a domain restriction. What is our domain of this function? Pi over 2. And are we inclusive or exclusive? Inclusive. And what about the range? -1 to 1 inclusive. And how do we then transition that to our inverse function? Flip them. 5. Yes, makes perfect sense. I get this. 3, sort of getting a handle on it. 1, I have no idea what you're doing there. My swoops are not swooping. Okay. How's that going to change for cosine? In other words, if we take a cosine curve and we visualize what a cosine function looks like as a parent function, what domain should we use that's contiguous and close to 0 that gives me all possible y values? This one's easier, right? We can just use 0 to pi. And what that means, the reason that's helpful to us is when we think about our unit circle, we're talking about values from 0 to pi. We're not going to use these values. And those look really familiar to us. So that's going to work great. Unfortunately, when we do sine, and we're going to be using this domain in our unit circle, which quadrants would that be? Not 2, because 2 is here. 3? Wouldn't 3 be over here? So it's 1 for sure. And it's 4, but like asterisk 4, right? Like if I came up with a value of -1, I'm not going to say, well, let's do a better one. Let's go like -1/2. What's the arcsine of -1/2? We know that that's going to look something like this. This is a pi over 6 angle. The reference angle is pi over 6. So should I call this 11 pi over 6 as quadrant 4? No, because I need to be in -1 quadrant kind of. So I would actually call this negative pi over 6. And if I were to, and that turns into -30, right? And if I did the arcsine of -1/2, it would give me -30, telling me that it's down here. It's not this angle, which is 330. True, the sine of 330 still gives me that -0.5, but that's not the one the calculator gives me. So when we do the cosine function here, again, we're going to go from 0 to pi. At 0, it's a value of 1. At 90, it's a value of 0. At pi, it's a value of -1. Concave down, concave up. Our domain is easier this time, 0 to pi, inclusive. Our range is the same, -1 to 1, inclusive. That means our arc function has 0, 1 as a point, which means 1, 0 is a point. It's got pi over 2 comma 0, which means 0 pi over 2. It's got pi comma -1, which means -1 pi. And again, this is our normal sine curve kind of oscillating around the x-axis. Now we expect it to be oscillating around the y-axis. So swoop it appropriately. That wasn't a very good swoop. Better swoop. And again, domain and range flip-flop. This time the range goes from 0 to pi, and the domain goes -1 to 1, inclusives. Questions? And we'll get to how we use this in just a minute. Last one in the same thread is an arctangent. So first we have to remember how a tangent graph graphs. What's the tangent of 0? Good. And if I go over 45 degrees and I take the tangent, I'm going to get a nice comfortable number, which is what? Good. And if I go -pi/4 or -45 degrees, -1, and then at these critical values of pi/2 and -pi/2, I get those asymptotes. Right? Those come from sine over cosine, which is 1/0, undefined. So I expect to be able to graph swoopiness is tight. I wish this had been scaled differently. So when I translate that to arctangent, I had an asymptote at x equals -pi/2. Now I'm going to have an asymptote at y equals -pi/2. And another one at y equals pi/2. And 0 point. And at +pi/4, it'll be at a +1. At -pi/4, it'll be at a -1. And again, I expect it to kind of swoop this way. Again, the swoop is quite hard with that particular scaling. What's our domain for tangent?
Oh.
Does this give us all the values? This is a complete period of tangent, right? Tangent's period is just pi. And if we go from -pi/2 to pi/2, that's a full period, and it gives us all the y values. So we're going to go from -pi/2 to pi/2. Good. Open circles. In other words, exclusive because of the asymptotic behavior at the ends. It never reaches those values. And what about our range? -infinity to infinity. And are those closed brackets or open brackets? Open always. Because infinity is an idea, not a number. And then the arctangent function just flips those. It has all real numbers as possible x values. And the y values are limited. They go from -pi/2 to pi/2 exclusive. Now, the whole point of this is so that you can correctly interpret arctangent, arcsine, arccosine applications. So flip to page 2, please. And this is what you're supposed to be able to do. Arcsine of 1. So let's take a unit circle. And if we're looking at the sine of theta, which quadrants are valid? In other words, we thought about this restricted domain in the sine function so that we could get a function in the arcsine function. Which quadrants was sine valid in? 1 and 4, kind of -1, whatever that is. But it looks like this, right? And we just have to remember these are the negatives. So if I'm looking for where sine is equal to 1, what would I get as an answer? 90 degrees or pi over 2, right? What about root 3 over 2? I'd look at my graph. Is that familiar to us? Have we done enough of these with unit circles now that we know that's a common answer? In other words, it's one of our unit circle values. Because sine is the opposite, that's the taller leg of the triangle. So this is going to be this one, which is what? 60 degrees or pi over 3 radians. What about the arcsine of negative 2?
That's not. You can't get it bigger than 1.
Good. Remember, our domain of the sine function goes from 1 to -1 to 1 to -1. It cycles around there. It never reaches -2. So this angle that has this ratio using arcsine does not exist. DNE does not exist. Take a look at number 4 here. Now we're doing the cosine. So we need a different vision. What quadrants are valid for cosine? 1 and 2. This one's easier for us. So when I see negative root 2 over 2, again, does that feel like a common unit circle value? It does. Which quadrant, 1 or 2? It's got to be in 2 because cosine is the x value. So we're saying negative root 2 over 2. What's that value? $135 or good, 3 pi over 4. What about inverse cosine of 3? Doesn't happen. Does not exist. What about arc cosine of -1? Here's +1. Here's -1. What is the degrees that would give you an answer of -1 in this realm? 180 or pi. Good.
So does the negative matter, or like the arc cosine matter?
You mean, does this negative with the 1 matter? Or do you mean
like if it was cosine of the negative? They're the same thing, but they're just written differently.
oh, this versus this? Yeah, those are the same things. Exactly. It's really like, doesn't this look like it should be secant? Is this the reciprocal of cosine?
Yeah.
But it's not, right? If we want to say reciprocal of cosine, we'll call it secant. We're not going to write it like this. This means inverse. All right, now we got to do tan. So we need our tan graph, really arctan graph. Which quadrants do we need for tangent? Which are valid quadrants for arctangent? 1 and 4 again. Which is the same as which? Sine or cosine? Sine. Do we have some other relationship using sine, cosine, and tangent where sine and tangent are paired up and cosine's an odd one out?
Yeah, and them being odd.
Even odd functions, right? Sine and tangent are both odd functions. Cosine's an even function. In the same way, sine and tangent as arc functions share the same quadrants, whereas cosine's different. So can we agree that root 3 over 2 is a common value we've seen when we take the tangent of some angle? Is this bigger than 1 or less than 1? What? Did I say something different? Sorry, root 3 over 3 is correct. Root 3 over 3 is the arctangent. In other words, if I take the arctangent of this ratio, there is one of our angles on the unit circle when tangented that gives me this. So what I like to think about is this greater than 1 or less than 1? Less than 1, right? Because 3 over 3 would be 1. Root 3 is smaller than 3. So if this is less than 1 and it's positive, we're in quadrant 1, and I expect my opposite to be smaller than my adjacent so that the ratio for tangent is less than 1. So what angle is that? Or what radian is that? 30 or 5 or 6. Good. What about the arctan of -1? Good. Remember that tangent achieves 1 at the 45. And because we're down here, the negative quadrant, where the tangent's always negative, we'd want to look at this 45-degree angle. So you could either say negative 45 or negative pi over 4. I mean, like 315? Because that would be you trying to create a window whereby your domain is split. You've got this gap in the middle of it. We're trying to create a contiguous domain. So we've chosen this to be our domain. You could have, right? But your calculators won't match that. So unless you're planning to like rewrite mathematics, you should just recognize that when you use your calculator and you do the arctan of -1, it's not going to give you 315. It's going to give you -45. And you need to expect that, know what it means when it comes up. Okay, arctan of √3, bigger than 1 or less than 1? Greater, it's up in quadrant 1 or quadrant 4. And it's the bigger triangle, which is the 60-degree triangle. So we could say either 60 degrees or pi over 3. 5, I get this. 3, I'm getting this. 1, I'm not getting this. Okay. All right, I see a couple of 2s. I'll come check on you guys in a minute. Here's how we're going to apply these. Application. A ship left port A. Here's port A. And sailed 60 miles due east. That's this way. For those of you that aren't familiar, north, south, east, west. What would you call this direction? Northeast. What would you call this direction? Good. South, southwest. And then this would be southwest. And what would this be? West, southwest. Good. Okay, so we traveled east 60 miles, arriving at port B. And from port B, the ship sailed 120 miles. This should be in, it should say northwest-ish. Because if you travel 120 miles and stop at a point directly north of A, that's a right triangle, isn't it? And so if you envision what bearing, how you turned your boat to go from here to there, northwest suggests 45 degrees, but could this be 45 degrees? No, because if it was 45 degrees and this is 90, this is 45, that's an isosceles triangle. That would mean this is 60 miles and this is 60 miles, and this would have to be what measure? Excellent. 60 √2, which is not 120. This is 60 times 2. So in other words, if we wanted to calculate this, let's go back to our SOHCAHTOA. Relative to this angle is 60 opposite, adjacent, or hypotenuse? Adjacent, and 120 is hypotenuse. Which of our trig functions uses cosine? So in other words, if I say the cosine of theta is equal to 60 over 120, in other words, the cosine of theta is equal to 1 over 2, how do I solve for theta? Arccos, or inverse cos. And what you get is theta is equal to the arccosine of 1/2. I can use my calculator for that. I'm going to say arccosine 0.5, and I get 60 degrees. So is my answer 60 degrees? Asterisk. You have to, when you use arc trigonometric functions, you have to consider what was really being asked of you, because it's forcing an answer to fall within these restricted domains for the arc function. Domains for the arc function, which means Yeah, sure, that's a 60-degree angle. That's a reference angle. But where are we traveling then? We're saying that that's 60 degrees. So how would you describe this direction? Good. I would agree that that's a rough way to pronounce it, north, northwest. But as long as we did the calculation, why don't we give it more precise name, right? Let's say exactly how to travel that direction. And the way you do it is you say, this is north and west. It's some combination of those, right? Is it more north or more west? More north. So we're going to start by saying north, but then we're going to qualify it. Well, it's not really north. Instead of going north, we're going to have to go an additional 30 degrees west of that. So it's north, but then a little bit 30 degrees worth west. Make sense? Odd, but yes, you're going to have to talk about bearings using this notation. So what if I were to say something like this and the angle were 10 degrees in there? If this was 10 degrees in here, we're going there, how would you describe that? Is it more east or south? So I'd start with east, 10 south. Don't call it south, 80 east, because 10 is smaller than 80, right? All right, one more example for you. We're running out of time here. Kicking a football, some theta degree angle. It's got to get 10 feet to get over the goal post, and you want to figure out what distances away it is. Create a function tying these together. SOHCAHTOA. What do we do? Opposite over adjacent, tangent. So the tangent of theta is equal to 10 over d. We got two variables, which is, okay, it's a function. So we write theta as a function of d. Ooh, how do we solve this for theta? Arctan. So theta equals arctan of 10 over d. And then it says, using a graphing calculator, find theta when d is equal to 75 feet. In other words, I'm going to write it as arctan 10 over 75, right? Same function. Do I go here and look for what value it is? I'm looking for where it's 75 feet. What angle gives me 75 feet? No, this works backwards, right? The angle is the y value. This is the angle. So if I want to find 75 feet, I got to go this way. So the x value is 75 feet. It looks like about 7.6. But all I have to do really is say theta is equal to the arctan of 10 over 75. You don't really need a graphing calculator. 10 divided by 75, 7.6. I'm sorry, I'm not showing you that. Sorry, guys, just did arctan of 10 over 75 is theta. On the calculator, that comes out to about 7.6. Please finish up this packet as your homework number 60. Thank you very much.
Thank you.